For a long time, individuals have imagined what life may be like in other universes. Because of the James Webb Space Telescope, it's the most astonishing telescope in existence. That question may finally be fit to be dissected, while noting the closest star system to us, Proxima Centauri, which is only 4 light-years away. Scientists have observed a few unequivocal peculiarities from one of the planets in the system. Proxima B, these irregularities, called artificial lights, have dazzled the mind of mainstream science. Yet, what are they? Do these lights propose the presence of intelligent life on that world? Join us as we investigate the James Webb Space Telescope's startling discovery of lights that could change everything. The only life that we are currently aware of has existed on Earth since before recorded development. People have long questioned whether there is life elsewhere in the universe. To conduct such an interstellar inquiry, American space specialists Jill Tartar and Thomas Pearson launched the Search for Extraterrestrial Intelligence, or the SETI, project in 1984. The Foundation's objective is to gather radio transmissions from outer space. Waves are able to travel farther and are more likely to be detected by the 42 radio telescopes that make up the unique Allen Telescope Array in the California Sierra Nevada mountains. Anyway, as of late, no definitive extraterrestrial signal has been found. Following that, the James Webb Space Telescope's successful launch supported the mission to examine a range of exoplanets circling distant stars. As the largest telescope beyond Earth, floating around 1 million miles from Earth and equipped with extremely well-appointed, delicate markers, it has the potential to uncover momentous discoveries. Back then, no known planets existed outside our planetary system. Anyway, since then, more than 4,000 exoplanets have been found circling various stars. As indicated by NASA, the universe may contain millions of early exoplanets. Signs of something happening beyond our planetary system may be found. Galileo's extraterrestrial vegetation spacecraft, on its course to Jupiter, turned its instruments back toward Earth and perceived an obvious indication of vegetation by seeing the vegetation red edge, a biosignature that consists of a blend of red and infrared light reflected by plants. For example, a planet like Earth covered in jungle should have a strong and easily recognizable red edge. The James Webb Space Telescope JWST will measure the red edge of distant Earth-like planets in the habitable zone around stars, which could provide critical insights into what's happening beneath the surface of an exoplanet's atmosphere. When daylight crosses a planet's star, the JWST could potentially detect it as it enters the planet's atmosphere. The missing frequencies would then be seen through spectroscopy as particles and molecules in the atmosphere absorb specific frequency ranges, creating a unique fingerprint that the JWST can recognize. This technique may be used to determine the composition of the atmosphere and whether life is possible. Life could exist on Earth-sized planets with atmospheres like our own, made of a mix of oxygen, nitrogen, and carbon dioxide. By looking for elements that aren't commonly present, we might be able to detect intelligent life. For instance, chlorofluorocarbons, CFCs, compounds designed for use in refrigeration and cleaning products, would almost certainly be detectable by extraterrestrials observing Earth's atmosphere from a distance. If the JWST detects CFCs in planetary atmospheres, it would be a decisive indication of mechanical advancement. But still, life on exoplanets may not look like life on Earth at all. Sometimes, even ordinary living creatures like extremophiles, species that can thrive in harsh environments where other organisms would perish, could seem extraterrestrial. These living microorganisms can survive extreme circumstances, like temperatures up to 250 degrees Fahrenheit or strong acids with pH levels under 3. Since planets like Earth are more likely to support life than those with extreme temperatures or acidic conditions, it may be wise to focus first on those ideal candidates. These planets could have temperatures that allow liquid water to exist on their surfaces, as well as orbit a stable star. Our Sun is considered a yellow G-type star. These stars are more limited in number and generally live shorter lifespans. However, in our universe, the likelihood of studying planets in orbit around red dwarf stars, which are more common and have lower luminosities and temperatures than the Sun, is higher. This longer timescale allows for the development of life and the evolution of complex organisms around 40 light-years from Earth. The TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It orbits a calm red dwarf star with 7 rocky Earth-sized planets. 3 of these rocky planets, located in the so-called habitable zone, could have liquid water on their surfaces. Despite its smaller size and cooler mass compared to our Sun, the TRAPPIST-1 star emits light, similar to Earth's Sunday light. Because of the planet's close orbits, the most promising chance to detect city lights outside our solar system may be Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun. Proxima is much dimmer than the Sun, so a planet would need to be much closer to it than Earth is to the Sun to support life. Due to the presence of liquid water, in August 2016, astronomers found a planet with 1.3 Earth masses in the habitable zone, like the one in the Goldilocks model, where the light intensity is ideal for liquid water. Proxima B orbits Proxima Centauri, but it is possible that Proxima B is an airless, inert planet. Considering that it orbits its red dwarf star at a mere distance of 4.6 million miles, this close orbit exposes it to intense solar winds that could strip away its atmosphere. Nevertheless, Proxima B gets enough sunlight for temperatures and liquid water to exist similar to Earth due to its proximity to its star. Proxima B is believed to be tidally locked, always showing the same side to the star, much like the Moon does with Earth. Proxima Centauri is around 18% the mass of the Sun and emits substantially less light, only 5% of the Sun's brightness. It could appear to be a barren, burned planet. However, liquid water could exist on Proxima B as long as the planet has an atmosphere to retain heat. Since the total energy received is only 65% of what Earth receives from the Sun, the planet may not be especially hospitable to life. Still, it remains the best candidate due to its tidal locking, which means it always faces the same side, toward the star, resulting in permanent day and night, with extreme variations in temperature. Additionally, Proxima receives nearly 3 times the amount of high-energy radiation that Earth does, including X-rays and ultraviolet light. Because it is close to Proxima Centauri, Proxima B is constantly bombarded by high-energy particles during solar flares, lest it has a protective magnetic field like Earth's. The conditions for life may not be ideal. Despite the favorable circumstances, models unfortunately imply that the atmospheres of tidally locked planets may experience rapid breakdown as a result of the loss of volatile gases on the night side. The atmosphere of the planet can be refilled by plate tectonics and volcanic activity. This is possible in the presence of strong magnetic fields. Such an atmosphere is less likely to escape, since we don't have substantial information on Proxima B's volcanic activity or magnetic field strength. We can't definitively measure whether the planet has an atmosphere. However, since an atmosphere suggests the presence of seas and both together suggest the potential for life, there is great hope to determine whether Proxima B has a complex biosphere. It might have solar-powered charging stations spread out across the day side to generate energy, lighting, and warming the side facing the night, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has sparked a rush to determine if it crosses its star's face. These transits, viewed from Earth, would allow scientists to determine the planet's size and mass, enabling them to assess its density and confirm its rocky composition, offering clues about the materials that make up its surface. During a transit, starlight could pass through the atmosphere of the planet. However, The likelihood that the orbit will be in the right alignment for scientists to observe a transit is only 1.5%. The star's tendency to erupt further complicates matters. Astronomer David Kipping of Columbia University states that the star is unstable, as solar flares cause a rocky planet to absorb sunlight and re-emit it as infrared light. However, rocky planets generate a particular type of infrared radiation, distinct from that emitted by stars like Proxima Centauri. The James Webb Space Telescope, JWST, was specifically designed to detect infrared light. Proxima B's infrared signature is critical to identifying the planet's atmosphere. Also, the JWST's infrared capabilities are infinitely better than Hubble's, which could allow it to detect city lights on the night side of Proxima B. Even if they are as weak as those on Earth, the JWST may be able to recognize artificial lighting if it can isolate signals in a frequency band much smaller than the star's light. Proxima B's dayside may be heavily covered with solar panels reflecting light from the star. As Proxima B orbits its star, it experiences a regular pattern of day and night with extreme variations in temperature. The temperature contrast between day and night will depend on whether the planet is entirely made of exposed rock. If it lacks an atmosphere, Proxima B's temperatures will vary dramatically, as the dayside will radiate all the energy it receives from Proxima Centauri as black body radiation. The night side, on the other hand, would resemble a frozen wasteland. If the temperature contrast between day and night is less pronounced, we can deduce the existence of an atmosphere. It will take the JWST just 11.2 Earth days to gather enough data to detect the first artificial city lights on Proxima B's nightside lights that might suggest intelligent life exists beyond our solar system. Given the study's conclusions, Proxima B may harbor hidden secrets. Perhaps the daytime of Proxima B generates abundant solar energy, and the lights could offer evidence of a vibrant and technologically advanced society, while the presence of artificial lighting on Proxima B would be a revolutionary discovery that scientists are cautiously pursuing. The detection of such lights could suggest advanced civilization. However, there are numerous additional possible explanations for these signals. The technology that the James Webb Space Telescope uses to examine distant worlds is still in its infancy, and astronomers are just beginning to refine their methods. The lights detected could be natural phenomena, reflections from surface features such as volcanic eruptions, lightning storms, or even unusual atmospheric phenomena that might imitate artificial lighting. It is essential for scientists to continue their research and cross-check their findings. In fact, the James Webb Space Telescope will keep an eye on Proxima B as well as other potentially habitable exoplanets to build a broader understanding of their atmospheres and surface conditions. The detection of artificial lights would also be followed by years of further exploration to confirm their origins. If the signals do indeed originate from intelligent life, it would represent one of the most profound scientific discoveries in human history. The excitement surrounding Proxima B and other exoplanets doesn't just stem from the hope of finding life. It also raises broader philosophical questions about humanity's place in the cosmos. The discovery of alien civilizations would force us to rethink the uniqueness of life on Earth. It could lead to an era of unprecedented collaboration between nations, as the discovery of extraterrestrial life would unite humanity with a shared sense of curiosity and awe. It would also underscore the importance of space exploration, pushing us to invest in new technologies that will make it possible to continue searching for answers in the distant reaches of the universe. For now, the search for city lights on Proxima B serves as a tantalizing possibility, one that may soon reveal whether we are truly alone in the universe. As the James Webb Space Telescope sends back more data, the desire to discover evidence of intelligent life beyond Earth becomes more real, drawing us ever closer to answering one of the greatest questions of all. Whether or not Proxima B hosts an advanced civilization, such a discovery could be the key to unlocking the future of space exploration and interstellar communication as we continue to push the boundaries of what's possible. The next generation of researchers, explorers, and astronomers may well be the ones to confirm what was once thought to be impossible, that life in all its forms is more common than we ever imagined.